So, okay, I will wait for a few minutes and we'll start the session. I'm so sorry, this time my session was rescheduled from Saturday 3 to 5 to this Monday 3 to 5. Hello all, I'm starting in 1 minute. I'm sharing my screen. Hello, all. Thank you for joining this session. So basically, the live sessions are meant to be as interactive as possible, and all the doubts that you are having in a week when you refer to the NPTEL lectures, uh, in this live session, we are supposed to solve all those doubts, and also some questions we'll try to solve related to that, so that you will have uh, the compatibility of solving the questions in your exams. So yeah, this is Annu from IIT Hyderabad, and this is the second week live session, the wireless and cellular communication. So basically, in the last week, we saw some of the basic concepts like how 5G emerged, how 3G emerged, what are the different spread spectrum techniques, and we also saw some of the Python codes associated with it. Because in week one, there was not much content to explore, but yes, it was good in terms of specifically some questions and solutions. But in this week, we what we saw is it's basically path loss based model, and it's related to questions accordingly. And there are some modulation techniques, how the energy is changing, and all those stuffs are there in this week, and that I'm trying to solve the problem. And we'll also go through some probability concepts and how it is used specifically for wireless communication. So starting from the network basics. So cellular network is composed of cells served by a base station. So if you have an area and that is divided into hexagonal cells, if we have gone through the lectures, so and that is served by a particular base station. The base station is nothing but a tower that you call. Okay. And the key formula is this, which Q is equals to root over 3n, where Q is the co-channel reuse ratio and n is the cluster size. So n is the size of the cluster. So what it shows is like we are having larger n reduces the interference but lowers the spectral efficiency. How? Because it is showing the skew and it is depending on the root over n. So you can directly say that Q is directly proportional to root over n. So if we have higher n, so obviously the Q is also increasing, which reduces the interference because here you are having the co-channel reuse ratio, but also lowers the spectral efficiency because the area will be congested and the spectral efficiency is directly proportional to C. And C is equals to B log 2 1 plus S. Now, a basic question arises here from this formula. Like people, even in the interviews, people ask about this. Uh, so suppose you are having B tends to infinity. So what will C tends to? Okay. So here, uh, ideally it should be infinity, right? Because here from C is directly proportional to B. So if B tends to infinity, C is also tends to infinity. But no, this is not the case. Why? But because in the last lecture we saw that B log to 1 plus S by N. Okay. N is equals to N naught into B. Okay. Where N naught is equals to K T. Okay. So here you are having C is equals to B log to 1 plus S by K T B. So what you can see here is C is not only directly proportional to B, but C is also directly proportional to log to 1 plus S by KTB. So what you get is if B tends to infinity, so direct is 1.44 S by S by M. It's not ideally infinity. C is getting tends to this. And the derivation you can it's ideally a homework. You can just search in the Wikipedia and get the derivation because the simple log 2 formula is there where is e power log 2 1 plus 1 by x there x log 2 1 plus 1 by x. So it is that value will give is 1.44 s by n. So this is very important for you to understand. And frequency reuse allows capacity increase, obviously. So hexagonal cells minimize the coverage gaps because there's a reason behind that. Gap is minimal. That's why, and it allows for the frequency reuse. That's why the hexagonal gaps are there. And C grows with smaller n. So because capacity will be there if the n is smaller. The size, uh, the cluster size, if it is less, then the capacity will be high. How you can see that? Because if the capacity, the cluster size, suppose is very large, so capacity at the same time you cannot serve to maximum users. And capacity is the maximum achievable data rate per user. Capacity is that. So if the capacity, if the n is very high, the cluster size is high, the achievable data rate will be very less per user. So that's why C will be less. Now, this is very important, and that's how in the week 2, most of the questions asked. So we have free space path loss model. Like the receive power is equals to PR is equals to PT plus GT plus GR minus 20 log 10 4 by 4 pi D by lambda. So it is all in dB. Whenever the sum term comes, then it is in dB. So I couldn't write, I'm writing here. So PR is equals to PT GT GR divided by 4 pi d by lambda square. This is the linear scale. So whenever you are converting into log, so what is that log? You take apply 10 log 10 because power is a square. So you do 10 log 10, or sometimes you do for power you use, if you want to convert power in linear scale to dB scale, then you do 10 log 10 power in linear scale. If it is simple quantity, then it is 20 log 10 if you convert. But why power here you do 10? Because it is square already. So you don't do this 20 log 10. So if we take this equation 1 into 10 log 10, both the sides, 10 log 10 PR is equals to 10 log 10 PT GT GR divided by 4 pi D lambda square. I'm writing here because we have space here. Then it is equals to PR is equals to PT plus GT plus GR minus, why minus? Because it is in the denominator. And since it is a square, so 20 will come. 20 log 10 4 pi D by lambda. Now you may ask, any doubt? El Sarala, any doubt?
No, madam.
So, yeah. So if you have any doubt, you can just interrupt me in between. That's it. So suppose this is what it shows as free space path loss. Free space means here the space is free, means it is simple air. Okay. So you have the transmitter antenna, you have the receive antenna. And since it is about the path, so it is about this path. This path. And we are talking about one path, but we saw that cellular networks are having different paths, which causes a multipath delay, multipaths fading. It causes the radiation fading, relay fading, and also we have shadowing, different types of interrupts. Okay, different types of interference. So this is path, and let's say path distances D between transmit and receive. So what it claims that you are having the receive power PR and the transmit power we know because we are transmitting anything, then we know the transmit power. And the gain of this antenna, because what antenna does, it's a transducer. It converts one form of energy to another form of energy. But antenna, specifically the RF antenna, what it does, it converts the electrical energy signal to radio frequency signal. Okay. And the simple conversion is antenna. But when you modulate, that is called modulation. But simple conversion, even if we speak to our phone, so do you know how many antennas are there in 5G phone? So I am having a 5G phone. The phone is from Realme. And do you know how many antennas are there practically? Have you ever wondered? So in practice, 5 antennas are there. So can you imagine just a small phone, 5 antennas are there? How it is possible? because of modulation. So with modulation, what happens? Modulation it does is like we are converting from low baseband signal to a high frequency so that the size of antenna reduces and we can convert to higher range. So just we have to reduce that much that this phone have 5 antennas. Okay, 5 antennas, and why 5 antennas? Through MIMO technology, because we want to direct the signal in a proper way so that no interference and no signal loss is there. So that is one of the application of that modulation. But even a single antenna is associated with a gain that is called GT. Okay, and this is also associated with GR. So this path loss, okay, since PR is directly proportional to PT, it is also directly proportional to GT. And since how much gain it can receive, it is also proportional to GR. Okay, but at the same time, it is not proportional to 4 pi d by lambda. Why it is d by lambda? Because as the distance increases, you will not receive the power at the same time. And since it is uh, C is equals to mu lambda, like mu is equals to that. So C is equals to lambda is equals to C by mu. Okay. So what I'm trying to say is like the frequency, it is inversely proportional to frequency. Okay. So it is inversely proportional to frequency, so it is directly proportional to lambda. Okay. So that's why it is 4 pi d by lambda. And this term, specific term, calculated based on the real values, based on this actual values. So this is based on some scientists, and they calculated 4 pi by lambda. It is giving that rough estimate. So that's why this is the path loss. And I'm sure that you will be getting 2, 3 questions on this in your exam. So that's why these are the important concepts. Lambda is equal to C by F. So loss increases with D square. Okay, it is used for line of sight scenario and basically for link budget analysis. Okay, so but for distance greater than dB, this is path loss dB. So if it is path loss, this term is associated with path loss in dB. Okay, so that's why PR is equals to PT, GT, GR minus path loss. Okay, and with this path loss, if it is greater than some certain instance, you should remember this formula. There is no other way to understand. But yeah, you should know why it is happening. So path loss at distance D is equals to path loss at distance dB plus 10n log 10 d by dB. So it is one of the breakpoint of path loss model where n is a path loss experiment, models two slow propagation, and n depends on environment. So suppose if the environment is uh, urban, so it is n is greater than 3. This is also like what it shows is like it is having two slope propagation. Suppose it is the path loss is for this distance is TV. So the path loss at distance greater than D, it will add. And what quantity it will add? The quantity is 10 log 10 n log 10 d by dB. So this is the extra term. Now, signal to interference ratio. So as we know, what is that? It quantifies the interference impact, and which is PR divided by all the other interference. Suppose you are having a receiver at this point and you are having the transmitter, but transmitter 1, transmitter 2. So this is required. Okay, so PR divided by the interference, whatever the interference you are getting from this and this. If it is I1, this is I2. So I1 plus I2. For co-channel reuse, which is calculated, is SIR divided by 1 upon DI by D0. The DI is what? Distance from interference distance. And this is a D0 divided by 10 minus N. So it is higher Q improves because highest frequency reduce coefficient reduce SIR used in frequency planning. And as we know, the signal to interface noise ratio is PR divided by PN plus summation of N, where PN is a noise power is KdB, which determines the link reliability. Higher SINR reduces the modulation, allows the higher modulation order. What does this mean? So what happens is suppose we are having the high SNR near to the base station, then modulation order means suppose the QPSK 16 form, 32 form, so which is having a better one. So as we know, 32 form is better than 16 form. So the 32 form will be having higher modulation order. That is called modulation and coding schemes. So based on this SNIR, we determine the base station determines a different modulation scheme to user one, user two, user three. So because since the environment is changing, so base stations have power and it determines that. Now this is important. The receiver sensitivity is the minimum power to achieve the target BER. Suppose the BER, which is a bit error rate, and the sensitivity means don't go with just name the sensitivity. Whenever the sensitivity word is there and with the unit is dB, then assume that it is a receiver sensitivity. So PS is equals to actually the noise power plus again. This is in dB. Whenever the plus term is there, you have to understand it is in dB. And bit error rate for QPSK, as we have studied in the digital modulation, it is Q of Q is one of the function, 2 EB by R naught. And what is the bit error rate for BPSK? It is Q of root EB by R naught. No, sorry, 2 EB by R naught only. What is the bit error rate for ASK? What is the bit error rate for FSK? So for FSK, it is Q over EB by R naught. But ASK is Q over EB by 2 R naught. And this is the basic formula we studied digital communication. Actually, one of you asked in the last class, one question was there. I think he joined or not. I don't know. One question was there where we have to find the average symbol energy. So average symbol, the constellation diagram was given last class. Question why I'm asking because he asked me last time and the doubt was there. So constellation diagram was there. It is 16 PSK 1444. Okay, and what was the question? The average symbol per energy was there. So how we calculated that question? We calculated that first we'll calculate the distance from the origin, and that will give energy per symbol divided by number of symbols. So 16 was there, and D1 to D16. That was the uh, formula. But the question was energy is directly proportional to D square. So why we were taking that directly D? So the answer is yeah, we have to take D square because energy per symbol is directly proportional to D square. We have to take the D square. And that question was wrong. So I checked it and I corrected it. Okay. So here the minimum receive power is PM plus SNR required. That is why I did SNR required. Like what is the minimum signal strength required to to decode the signal, because suppose I am having a phone. My phone, if you check in your specification, every phone is having this receiver sensitivity. So that is a minimum power to achieve the target PA. So lower PS implies better receiver. Like if the sensitive if the receiver is good enough that even a small signal comes, it will detect. So that's why lower PS is better. For example, if you go to buy a simple power amplifier or antenna, you always see which is having the best receiver sensitivity or which is having the best lower receiver sensitivity. The ideally it is minus 90 dB, but you should know that, and which we should consider while buying the phone also. Okay, SNR required from the modulation BER curves. So you have SNR. And this is a bit error. Can anyone tell me what is the? This is the curve, basically. Now fading in the fading margin. So fading reduces the random variations in PR, that is a receive power. Understood, right? Like some theoretical questions will come from this PS receiver sensitivity. If it is asked, it is required some multiple choice questions are there. Like last year, some questions are there. If it is the receiver sensitivity will be low, should be low, or it is depending on the depending on the noise power, or it is depending on the SNR. So it is directly proportional to SNR as well as PA. And it is like to achieve the target behavior. So fading introduces a random variation in PR. So to mitigate that, there is a fading margin, and that we called it as a MF. So if you have two type of fading margin, like slow fading and the fast fading. So fast fading is basically through multipath, like we're having different multipaths. So that question will also come, like fast fading is through multipath or shadowing. So slow fading is for shadowing. Shadowing means reflections. So there's a slow. Fast means rapidly the different parts are there. So it will be fast fading. This is very, very important. Some questions directly came from that. Freeze noise figure formula, like the noise figure for the casting, it is case. For example, you have an amplifier 1, amplifier 2, amplifier 3. So if you have noise figure of F1, so what will be the F? So formula is F1 is equals to F is equals to F1 plus F2 minus 1 divided by G1. This is the gain of cascade 1. This is G2, this is G3. So F2 minus 1 divided by G1 plus F3 minus 1 divided by G1 into G2. So where F is in the linear scale, where G is in gain, and first stage dominates F as it is directly proportional. Plus. So all the F are in the linear scale. F is equals to F1 plus F2 minus 1 divided by G1 plus F3 minus 1 divided by G1, G2. Multiple access and duplex techniques, like we have TDMA, CDMA, and FTD. So duplexing, there's a difference between techniques and duplexing. So this is a multiple access technique for the frequency or for the resource allocation. These are the techniques for the resource allocation. Like we have to use the resource, and resource is what? It's bandwidth and time. Okay, but here the duplexing is like you have base station and you have user. If the base user is communicating uh, to base station, then it is uplink, and if the base station is uh, giving signal to user, it is downlink, uplink and downlink. So if the uplink and downlink frequencies are divided, it is FDD, and if the uplink and downlink frequency are divided in time, then it is TDD. So that is the difference between duplexing and uh, the techniques. So, and also the GSM, the frequency band. So it is having a defined frequency band, which is F uplink is 890 plus 0.2 n, where F downlink is 935 plus 0.2 n for any channel n, where n ranges from 1 to 124 for GSM 900. GSM is used in 2G. Uplink and downlink frequency are separated by 40 to 45 megahertz. You should know, that's why I have created a slide for that. And yeah, this is very important, probability basics, because probability is everywhere, and one of the main uses of probability is in communications. So we know the basic what is probability. Probability is actually a metric to 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 define how certain the event is. Suppose a red ball is picked from a bag where the set of balls are there. So what is the probability? What is the metric or the certainty of getting that ball? So that we define terms from 0 to 1, and that is called probability. Okay, so again, if you have two events A and B, so if it is union, that is PA plus PB minus PA in direction B. So it is A or B. This is A and B, like happening at the same time, or it is happening both. Like the probability of getting a head or tail. Okay, a probability of getting head and tail at the same time, it's P of A intersection B. For independent events, what do you mean by independent events? So suppose you are the sample space of two different events are different, then it is independent. For example, I'm tossing a coin one time and second time. So are they dependent? Obviously no, right? Because the sample space of tossing a coin in one time is just one space, where sampling a second time is another space. The space of first is not affecting the other space. That is called independent. Suppose it is affecting the other space, then it is a dependent. Okay. So there's another term called mutually exclusive ones. So Mutually exclusive events means if the sample space of one is affecting the sample space of other, then it is mutually exclusive. Anyway, you can just go through some basics. Otherwise, it's fine. For independent events, this is P of intersection A and B is P of AB. Can anyone tell me what is the probability of A intersection B for mutually exclusive events? It's zero because P of A intersection B is 5. There's no similarity between that. Through sample space, I can tell that if you have A, if you have B, it is independent. Sample space itself is different. Okay, it's independent. And if we have same sample space but no similarity, it is mutually exclusive. Okay, so here P of A intersection B is equals to P of A into P of B, where here P of A intersection B is equals to 0 or A intersection B is equals to 5 empty sets. Another term is expectation and variance. So we have for a random variable, what you call by random variable. So random variable is actually a function that maps from omega to 0 to 1. What is omega? Omega is set of outcomes. Any random experiment. What do you mean by random experiment? Any random experiment tossing a coin, suppose gives H and T, and you map to either 0 to 1. So this mapping is called X. Okay, that maps from this is to 0 to 1. Any value, so not 0 to 1, this real line. Any value to real line. It can be 3 or 4. So it gives mapping from 0 to a real line. Okay. So if I'm giving 0 to 1, for example, we're having X is equals to 1, 2, 3, 4, 5, 6, and we are giving mapping to we are giving 5, 6, 7, 8, 9. This is also a random variable. Okay, so if we have random variable, it is defined by expectation and a variance, and this is a PDF. So if we have PDF, what is that PDF means? D of dx, f of x of x. This is CDF. So CDF means that probability of x less than equals to x. But it shows that the value of x, the random variable, is less than particular value, then it is PDF, the CDF. And the differentiation of that is called PDF. So expectation of any x is summation of minus infinity to infinity x of x of dx. And the variance is e of x square minus e of x of square. And this expanding, it will give that value. Shall I expand for you? It's okay, I will not do that. There are different types of random variable distribution. So if you have Bernoulli, so you have P of x equals to 1 probability, where P of x is equals to 0 for 0, 1 minus P probability. Like if you have Bernoulli, means two events are there. Okay. So either if one event is happening through uh, one experiment, and that is called P with probability P. If it is another is happening from 1 minus P, that is x is equals to 0. So if we can keep the random variable in two values, that is called Bernoulli. And once you repeat that two values for certain amount of time, okay, so that is called binomial. So what is a critical example of that? Like suppose you are getting tossing a coin one time. So it is having only one outcome, H and T. And if you're repeating one time, two times, three times, four times, or any number of times, then it becomes binomial. So that is the difference between Bernoulli and binomial. And the binomial distribution, if you want to find for any, suppose you're getting how many times you're getting the H in n number of times, or in n number of tossing a coin, suppose you're tossing a coin for 10 number of times. So here small n is what? Capital 10. And tossing a coin. Suppose you want to get the probability of getting head 3 times. So it is 10, 3. Probability of getting a head is 1 by 2 into 3. Probability of getting 1 minus is 7. So this is the probability of getting head 3 times in 10 trials of tossing a head. So using counting combination and probability of each sequence, it used to model package success probability. Like it is just a package of what is the success of getting head. So that is 1 by 2. And hence you can do that. Again, there is another type of distribution. Now we saw a binomial and binomial, Bernoulli and the binomial. What is Poisson? Suppose you are having a rare events. Suppose in a population of 1,000 people, and one of them is getting dengue. So that is a rare, okay? And what the quantity you are getting, mean means expectation. And then getting a dengue is a random variable, okay? And mean is expectation, that is lambda t over a period of time. The probability of k arrivals, like how many people are getting, is nt is equals to limitation of n tends to infinity, n k when we do is tends to infinity, okay? It's also similar to binomial, but when in the n tends to infinity, that you get is lambda dk, because here if you are having a mean e of x is equals to lambda t, then probability small p of getting that thing is expectation divided by n. How many people are getting? So it is lambda t divided by n. So it is small p. Okay? And 1 minus small p power n minus k. How many people? This derivation uses a limit of binomial expression and this models random call arrivals in a network. Random calls. So what it shows is like Bernoulli was there. When we repeat for n number of times, it is binomial. Now, when binomial, the number of experiments tends to infinity. Okay. And that is called binomial. That is called Poisson. It will tends to Poisson distribution. Now there's a term called exponential. Now I hope you are understanding, but uh, even if you're not understanding, so these are some discrete type of events. Now you may ask whether it is discrete or continuous. Why I'm asking it is discrete? Because you are doing summation here. So not here, but yeah, in the discrete type of experiments, you will do the summation. In continuous type, you will do the integration. That is the only difference. But here, why I'm asking it is discrete? Because you can quantify different values. Okay. But in continuous time, do you know the probability of x is equals to k is what? It is actually 0. In continuous time, you can only quantify with respect to range. For example, probability of x is equals to x lies from k1 to k2. That is integration from k1 to k2, fx of dx. This is probability density function. An exponential distribution is intervariable types. The time between Poisson intervals events are exponential. This is discrete in nature. Suppose a dengue person comes here, comes here. So the time difference is actually exponential. So if f of t, so CDM, where p of t less than equals to t is equals to 1 minus e power minus lambda t, where if you differentiate it, d of ft divided by dt, then it is minus lambda minus e power minus lambda t. It is e power minus lambda t. That is why the time difference between the Poisson intervals is e power minus lambda t, where the if p of t equals to t, with zero events in T in a particular time interval. What I'm saying, you say in a particular time interval, it was T, right? So the distribution of T, here we are trying to find the distribution of T, is actually exponential in nature, and that is lambda e power minus lambda T. There's a very beautiful theory of this probability, and why I'm telling, I'll tell you later, like gradually can going to the point where this in communication it is used. And in subsequent lectures also you'll be using that. Communication without probability is nothing. Okay. Now we have seen different type of fading techniques. So what we have seen through multipath, fast fading was through multipath, whereas slow fading for the shadowing. Okay. So in fading also multipath, there's different types of fading techniques, and that is called first is relay fading. So if we are having a non-line of sight, so for multipath without line of sight, the channel gain is given by root over x square plus y square, where x and y are the Gaussian noise. So using the transformation of random variable, you are getting FR is equals to small r divided by sigma square. Like I wanted to tell you different, if you combine two different x square plus y square, just x and y are both are random variable, and that to Gaussian nature, then you are getting this type of distribution. The integration over angle gives Rayleigh PDF, and the receipt power r square is exponential. So this is the PDF of receipt power r. So how will you get the receipt power r square? So if you want to get the receipt power from, suppose, one range to another range, r is equals to d1 to d2. So we have to do the integration dr, and this is the receive power. And if you want to do r square, then you have to do r square. So you have to integrate over that range from one to another range. And then using this PDF, you can easily get the receive power when the fading is Rayleigh fading. And what is the beauty of this is, like in the Rayleigh fading, you are having without line of sight. Now, radiation fading. Suppose you are having one antenna here, another antenna here, there's a line of sight is there, then it is called radiation. We should know the distribution of every fading technique. So that's why I'm telling you. So root over r x square plus y square is one of the r channel gain. Okay. So if the x and y are Gaussian in nature, and you're getting e power minus r square divided by 2 power 2 sigma square. Okay. When we are having a deterministic S and scattered gate Gaussian component, then you're getting in this term. And it uses Bessel function from polar coordinates integration k factor. So if you want to calculate the receipt power, which is R, from R to R2, it's just an integration from R. This is a continuous line, but this is complicated as compared to this. Okay, that's why it is root over x square plus y square, because you're getting x here, you're getting y here. It's not line of sight. So if line of sight is there, then you have to root over x square plus y square, and you're getting Rayleigh. But if it is line of sight, then you're having deterministic coefficient is S and scattered Gaussian component, and that is f of r. Okay. Now this is very important as a Gaussian noise model and EWG, all are function of random variables. Okay, so all are functions of random variables. That's why I started with a random variable, and each random variable is characterized by, that is characterized by expectation and the variance. So variance of x is actually e of x square minus e of x. This is MSV, mean square value, and this MSV is actually the power. The variance is the sigma. Sorry, sigma square. The standard sigma is standard deviation. It is variance by x. So thermal noise, that is by default AWGN, the additive white Gaussian noise, and it is having zero mean and sigma square as a variance. So every random variable is governed by this. And if it's a Gaussian, then it is 1 by root over 2 pi sigma square e power n square minus 2 sigma square. This is another formula that you have to remember by heart. So 1 by 2 root over 2 pi sigma square e power minus sigma square by 2 sigma square e power minus x square by 2 sigma square. This is the Gaussian. So if you solve it, what you're getting is, if you integrate any PDF, so it's not like this is integrating and will give the one. No. So integration of any PDF minus infinity to infinity x is equals to 1. That is a beauty because this is the probability density function. So if we have, what does this mean? So this, if it is having fx, some function is there. Okay. If you integrate from minus infinity to infinity, you will be getting 1. Or you can say the area under PDF is 1. Okay, so that's the beauty, and that's why it is called probability density function. And also, the value of lies between 0 and 1. P of x is equals to x lies between 0 and 1. And this is the integration of minus infinity to infinity over x fx of the 2's. Like it should lie in the range. Any probability value should be equal to from lie between 0 and 1. So this is, if it is there, then it's called Gaussian normalization, which underpins AWG and channel. There's another concept called Markov state derivation, where if you have different channel states S1 and S2 with the transition probability Pij, the state vector pi, which shows from one to another value, that is pi p is equals to pi, and you know ax is equals to lambda x. I'll just tell you the basic formula. So this is the matrix. Okay, I'm telling you the concept of eigenvalue and eigenvector for 5 minutes. So this is the matrix. And matrix is what? Matrix is nothing but the mapping from input to output. What is that? So we have 1, 2, 3, and if we have 4, 5, 6, and this mapping, it's called matrix. Suppose 1, 2, 3 you're getting. Then 1, 2, 3, 1, 2, 3. So if you map 1 to 1, you'll get 0.5. If you map 1 to 2, all the permutation and combination, you'll get 0.6, 0.7. So this is a mapping. This is called A. This is a matrix. Okay. The matrix is nothing but a function from input to output. Okay. Now you have the function. If it is multiplied with any vector, suppose any input is there, that is called x1, x2, x3. Okay. And you are getting the same vector x1, x2, x3 with some scaling vector or some scaling factor. So we had ax is equals to lambda x, isn't it? Now we are having a is equals to, suppose, some 1, 2, 3, 4, 5, 6, 7, 8, 9, and x is equals to nothing but its vector, x1, x2, x3. And this is lambda. Lambda is nothing but any scalar. Okay, and you are also getting x1, x2, x3. What does this mean exactly? What does this mean? As I told, this is just a mapping, or you can say it's a rotation from 1 to 2, A. Okay, this is X and this is Y. So the mapping from A is nothing but mapping from Y, X to Y, right? Now this mapping, if it is multiplied with any vector or any X vector, if it is multiplied, A is multiplied with any X, then you are getting the same vector if scaling factor of lambda or any scalar, or let's say lambda is equals to 1 for the time being. So suppose you are in Cartesian coordinate and you are having x1, okay, and it is transformed to, suppose it's x2, and this is the A. The transformation is A, and if it is multiplied with any vector, this A, and the second case is x1, and the transformation is A, and you're getting some multiplication of x1 only, and this is the transformation is A, and you're getting x1 only, lambda. So the transformation after transformation, A of x is equals to you're getting A of x and lambda x. Okay. So this particular transformation is called eigenvector. So you're multiplying a matrix with a vector that doesn't change its orientation. Okay, that doesn't change its orientation. That is called eigenvector. And but scaling factor by which it got scaled, that is called eigenvalue. It's a very beautiful concept. Suppose you are having a bottle and it is transforming, suppose it is having one function and it is multiplied with such one vector that doesn't change its orientation. Okay, it is not changing. Okay, it's staying the same way. And what is called? It is called one of the x's. So that x's finding is called eigenvector. So the vector by which it is multiplied and doesn't change its orientation is called eigenvector. And the factor by which it is multiplied and it's called eigenvalue. Okay, so this is very important concept, and this and you know what are practically those available vectors? It's a x-axis, y-axis, z-axis. Because if you multiply with any transformation variable, you will get the x-axis only. Okay, y-axis, z-axis, and that's why we name it as a basis in linear algebra term. And here it's same. For suppose we are having S1, S2 different channel states. Okay, and with the probability transition matrix of Pij. So if we and these are the left eigenvectors. These are the left eigenvectors. Why it is left? Because it is left of the transformation matrix, that is A. Okay, but once when we have uh, right side of this, it is called right eigenvector. And lambda is fixed, which is 1, unity. So solve the eigenvector for eigenvalue of 1 for P, which is used in Gilbert transform, and you will be getting state vectors as pi. It's very, very good concept. Okay. So outage probability distribution derivation is like if the outage occurs, when the outage occurs, when the SNR goes below some threshold. So if SINR is having the CDF of F of SNR of lambda, so if the P of outage is probability of the SNR goes to less than lambda, sorry, I'm telling, is less than the threshold of SNR, and that is called CDF. So if the SNR is exponential with mean, so we know that the CDF of that is 1 minus e power minus pi. This is nothing but lambda. I hope you can relate with this here. Okay, when it is less, it is exponential lambda e power minus lambda t, and then you were getting ft of is equal. So this is outage probability. See how it is used. Uh, different distribution, how it is used in practice in communication system. So it is outage probability distribution. 1 minus lambda t. So, and here, since it is greater than lambda t, so it is lambda is nothing but e power minus lambda t h divided by square. Now, I'll go through some transformation basics. Suppose you are having two different random variables, y is equals to g of x. Then PDF is having this f of x, and if the PDF of y is calculated, like have you seen that r is equals to root over x square plus y square, and you know the PDF of x and y, how will you calculate the PDF of r? Okay, so we saw that it is e power minus r square by 2 sigma square, somewhat like that it was there. But how will you calculate if it is simple function? So the PDF is equals to the simple formula is, how can we say that? F of y less than equals to y is equals to bytes g of x. So f, this is CDF I'm trying to calculate. CDF of y, which is nothing but f of y, that is p of g of x less than equals to y, which is equals to p of x less than equals to g inverse of y, which is equals to f of x g inverse of y. This is period, right? Now, if you want to calculate this, okay, this is CDF of y, right? This is CDF of y. Now, if you want to calculate CDF of y, capital Y, how will you calculate? As we know, this f of y is equals to nothing but differentiation of y of y. So it's nothing but f of y. It is capital here, it is small inside. D of dy, d of x less than equals to g inverse of y. It is nothing but yeah, so it is nothing but f of x of g inverse of y and differentiation of dy, g inverse of y, f of y. This is what here it is. Since we are taking only positive value, so it is also random variable cannot hold a negative value. So that uh, modulus function is there. Okay, I hope this derivation is clear, simple. You should always start with the CDM. Now this is change of the variables in integral. Suppose you are having y is equals to ax plus b. Y is equals to ax plus b, and we know the distribution of x. So how will you calculate y distribution? So simple formula, don't go with the formula, simple f of y less than equals to y equals to f of, sorry, b, f of y. I'm calculating first CDF, then we go to PDF. Ax plus b is equals to y. P of, since y is x is known, so I'm calculating that y minus b divided by a. So if the x is uniform distribution, if x is uniform, 0 to 1. So how will x look? 0 to 1 x, and this is f of x. This is x and this is 1 because area should be 1. Now I'm asking how y will look. Okay. So x, if it is x is less than equals to y minus b by a. So suppose if it is y is equals to ax plus b. So if the x ranges from upper limit is 1, okay, if the upper limit is 1, then the y upper limit is a plus b, right? If x is 0, y upper limit is b. So y will range from a plus b, sorry, b to a plus b. This is y, f of y of y. This is y. Now the question arises, how will you calculate small f of y of y? So as we know, just differentiate this uh, f of x, because if we differentiate it, it will be f of x y minus b by a. And if we differentiate with respect to y, so it is 1 by a. So 1 by a fx of y minus b by a. So it will start, the y limit is b. So f of y by b is nothing but 1 upon a f of x of 0. So f of x of 0 is 1. So it is 1. And calculating f of y of a plus b is 1 upon f of a plus b minus b divided by a. It is 1 by a f of x of y by a, 1 by a f of x of 1. So 1 is 1. So yes, it is 1 by a. This 1 by a. So here you are having 1 by a. Okay. So how can you write here? F of y of y is equals to 1 by a, 0 otherwise. So y ranges from b to a plus b. I hope this is clear. We should know how to calculate. Let me check with the actual data. Nobody calculated or what? Ah, see, it is that only y minus b by a. So 1 by a should be modulus, I forgot. 1 by a f of y minus, and how it will look like. It is very, very important. Trust me, it is very good also to understand. Mhm. Now, moving to the next part, the power of Gaussians. Like for x, r square is equal to x square plus y square. Then using the joint PDF and polar coordinates, it is 1 upon sigma square e power minus z divided by 2 sigma square. Like, I will tell you one thing. R square is exponential in nature. I'll tell you one thing. So in Gaussian, what you saw is f of x is equal to root over 2 pi sigma square e power minus x square by 2 sigma square. Isn't it? This is also exponential, right? But once we talk about the Rayleigh distribution, transformation for power of Gaussian, this is coming z, let's say z. 2 sigma square e power minus z divided by 2 sigma square, where z is greater than or equal to 0. So Rayleigh distribution, what you are seeing is it's only for z greater than or equal to 0. So e power minus z by 2 sigma square, and it is not square, it is exponential. So even Gaussian is exponential. Even Gaussian signals are exponential in nature. But the Rayleigh distribution is, this is r square. Okay, r by sigma square e power minus r square by 2 sigma square. So since r is greater than or equal to 0, here also it is r greater than or equal to 0. It is this. And if it is r square, then no power is there. Non-linear transformation is, suppose y is equal to g of x is many to one. So many to one means you're having 1, 2, 3, 4. Many variables are going there. And the sum contributions are like, it will be summation of f of x of xi, d of xi divided by d of y, where xi is g of my inverse of. He just gave me 2 seconds. And for example, y is equals to x square. Many to one, suppose one is also mapping to, two is also mapping to two, sorry, two is mapping to four, minus two is also mapping to four. So it's two variables are mapping to same frequency. So it is, and here you will be having some Jacobian for multivariate transformation. Suppose y is equals to g of x. So f of y, this, if y is equals to function of x1, x2, xn, then d of dy, x1, x2, xn. It's called Jacobian matrix. It does is d of y of d of x1, d of y is d of x2, d of y is d of xn. This Jacobian, where J is a determinant of Jacobian matrix. Determinant, why? Because we are this one. Suppose y is x1 square plus x2 square plus x3 square. So Jacobian matrix is what? D of y divided by d of x1, x2, xn, x3, sorry. So here it will be d of x1 square plus x2 square plus x3 square, d of x1. It is d of x2 plus d of x3. If you are having the ratio of random variable, the joint PDF will be calculated as integration of mod of y, f of xy, the ratio of two Gaussian is to Cauchy distribution. I'll give an example. Jacobian matrix. Second. Suppose the problem is I'm taking from the reference book, like Populous, very good book is there. So the question is, I'm taking the question that x, y be a pair of continuous random variables. with the joint period as f of xy, which is x or y, defining a transformation such that u is equals to x plus y, v is equals to x minus y. So what is the problem statement? So problem statement is find uh, find the joint period f of fu uv using Jacobian transformation. So let solution is let u is equals to x plus y, v is equals to x minus y. So what x tends to x is equals to u plus v divided by 2, y is equals to u minus v divided by 2. Computing the Jacobian, because here the Jacobian was computed for x. D is equals to d, which was known because it is known, x divided by, so yeah, j is equals to del of x divided by del u, del of y divided by del u, del of y, sorry, divided by del v. What is that? It is Jacobian of x, y, u, v. Okay, because what we were doing is like we were calculating f of x divided by f of y, right? But here we have multivariate function. So what we'll do is we are having multivariate function, like we're having function of x, y, u, v, f of x, y, del of u, v, right? So that we call it as Jacobian matrix. So let's calculate del of x by del u. So it is what it is. It will be 1 by 2 because here simply it's said it's 1 by 2. It is 1 by 2. It is minus 1 by 2, right? Modulus of j is nothing but minus 1 by 2 and 2 1 by 2 minus 1 by 2 1 by 2. It's minus 1 by 4 minus 1 by 4 just 1 by 2. Okay, it is as simple as this. Now here we were doing. Okay, so it is J inverse. So mod of J inverse is equals to 1 by 4 is 2. So f of uv is equals to uv, f of xy, u plus v divided by 2, u minus v divided by 2 into 2. And with simplifications, you can get it. So final answer we are getting solution it is stuff. It is 3 variable Jacobian matrix. Fine. Back to the solution. Sum of independent random variables, you can easily get that convolution part if the random variables when it will be the sum when it is granted in a cascaded manner. So if we have distribution f of x here, f of y here, then f of z final is nothing but z is equals to f of x convolution with f of y of y. And that is called in linear series random variable plus convolution. Sum of two exponential gives a non distribution. Maximum of random variables, it's selection combining. We'll see later. Minimum of random variables use outage calculations. Logarithmic sales, ignoring the steps. Inverse transformation, inverse channeling, outage probability, fading. This is Rayleigh distribution. So if we transform R to R square or receive power, exponential billion models of power relation. And this is outage probability and this BR analysis. So I think I'll go to the questions. There are some questions and answers. We'll go through that. These are some questions I have prepared based on probability. First, before that, I will go through the last 10 questions. A relay transmits at PT is equals to 10 milliwatt and minus 20 dB watt. It's milliwatt, okay? It is equals to minus 20 dB watt. And a user measures power PR is equals to minus 90 dB watt. The carrier frequency at FC is equals to 900 megahertz using free space path laws calculated resistance T. How will you calculate? The free space path loss? Nothing but PR is equals to PT minus 20 log 10. Since here there is no information on GTGR, you will assume that it's zero. So that's why I have not taken. For example, you may not have any receive again. So C lambda is equals to C by F, and using the formula, you'll directly solve and you'll getting 84 meters. So imagine with the power of 10 milliwatt, you're getting the distance of 80 meter, and the receive power sensitivity is minus 90 dB, and the frequency is 99. Second question is a base station transmits 1 watt signal to an amplifier that is having a gain of 10 dB. Output passes through a cable of loss 6 dB to an antenna gain of 10 dB. I find the isotropic radiated power. How will you calculate? Just think about it. You have to put in the formula for sure, but at least we should think before just jumping into the question. So effective radiated power is, as we know, basic Pascal formula. Cable loss should be negative, like should be divided. So EIRP in linear scale, it's directly proportional to PT gain GR or the amplifier divided by path loss. So if you convert into dB, it's just PT plus J amplifier plus GR, sorry, the G amplifier minus LC, and that is here, 14 dB watt. Now the question is receiver sensitivity for QPSK. Suppose you are having 5 gigahertz WLAN, wireless local area network, the bandwidth of 20 megahertz. Noise figure is a 66 dB. The QPSK modulation is used and the target BER is 10 power minus 5. How will you calculate the receiver sensitivity? Just think about it. How will you calculate? So, first of all, it is asked what receiver sensitivity. And what is receiver sensitivity? By definition, what we'll go through, it's minimum receive minimum receive power required to achieve a target BER. BER is given. And we know that BER is nothing but Q of root over 2 EB by N naught. Now, N naught is what? N naught is directly proportional to noise figure. Okay. So EB by N naught, let's see that. QPSK BR we are having. BR is equals to Q of, this is a function. Q of root over 2 EB by N naught, but BR is equals to 10 power minus 5. EB by N naught is this point. This is from the curve. With BR of this value, the EB by N naught will be a 9.07. Like you'll keep here and EB by N naught you can calculate. So from Q inverse, you can just check the Q function. Q function, I will tell you it's important. Function. The tail distribution of the normal Gaussian. So what it does is like, so we know, I'll tell you how to remember this because you often get confused. So we are having a Gaussian function. Gaussian function, we know that. What is that? F of, since it is continuous, so I'm talking about f of x is equals to root over 2 pi sigma square e power minus x square by 2 sigma square. Okay, this is if the mu is 0. Okay, and variance is this sigma. But suppose it is having a mu. So let's say it is root over 2 pi sigma square e power minus x minus mu square by 2 sigma square. Okay, if it is mu value is there, so it is not 0. Now the Q function is what? Q function is Q of x is nothing but probability of x greater than equals to x naught. What is that? It is equals to x naught to infinity 1 upon root over 2 pi sigma square e power minus x minus mu square by 2 sigma square. So what do you expect? X naught. X naught is suppose any value here. So can you tell me what is it a decreasing function or increasing function? So Q is function from here. So first of all is Q is a decreasing function. First point. Second is it is a tail distribution. So that's why whenever we are having a BER of 2 EBY naught, the BER of ASK, amplitude shift gain, ASK, and frequency shift gain. It is BER of 2 root over 2 EBY naught. FSK is root over EBY naught. ASK is Q of root over EB by 2N. So that's why BER of PSK is less than BER of FSK less than BER of ASK. So BER of amplitude shift gain is the highest. Middle comes when we are having the frequency shift gain. So essentially, the area under the Gaussian probability distribution function from given point to infinity is actually the Q function. And with the standard normal distribution, the Q function is already associated with normal distribution, like the mean of 0 and the deviation of 1. So here the Q1 means 0. That is the Q function. It calculates the probability of a random variable, which is specifically from standard normal random variable, which is greater than specific value, which is also called tail area of the normal distribution. This is Q. Okay. So using Q, you can have this. And the SNR, is nothing but 2 into EB by N naught. Why 2? because it is a QPSK. So in one QPSK, you are having, in one symbol, you are having 2 bits. So just multiplied with 2, 2 power n, 2 power 2, 4 symbols you are having. In one symbol, you are having 2 bit because it is energy bit. It is bit energy per noise power. So with the energy bit is multiplied with 2. The noise power, Pn is equals to 10 log 10 KTB B plus NF. So I told you, since the noise power is directly proportional to noise figure. Okay. And you may ask, what is a critical definition of noise figure? So what do you think? Noise figure should be high or less? Low? Since it is directly proportional to uh, noise power, it should be low, right? So it is actually the measure of how much a device, or like an amplifier receiver, degrades the noise to signal ratio. So it quantifies the amount of noise added by device, because suppose a noise created by any uh, electronic device, that is a thermal noise, and it is nothing but it's a KTB. Now you may ask, like, in that device, what is the scaling factor it actually gives? So it is given by noise figure. It should be less. Okay. The ideal noise figure, it's around 5, 6 dB. Okay. A lower noise figure indicates that a device adds less noise because it is proportional, right? So that is what it is, a unitless quantity. That's why it is dB, that degrades how SNRs. So that's why in linear scale, Pn is equals to noise figure multiplication with KTB. So in NDV, it is plus, right? So this is plus. And sensitivity is equals to, with the simple formula, PS is equals to PN noise power plus SNR. And this is nothing but this one. Because receiver power is nothing but the minimum received power, or the power required to achieve a achievable bit error rate. This is a very good question and can be asked. Okay. And 2 is multiplied because it is 1 bit energy. I hope you understand. Using the results from question 3, P is equals to this one. Transfer power is this one. GT, GR is this one. Link margin is this one. Find the range D. How can you calculate? Link budget formula. Let's see. Link budget is equals to PT, GT, GR minus path loss minus margin is equals to PS. It is a receive power. PR, sometimes PS it is called. The receiver sensitivity, when it added with PN plus SINR, it is PS. Sometimes it is called PR, the receive power. Both are same exactly. Substitute this one, and the path loss is this one. A free space path loss is this one. Solving it will be getting this. Okay. Now, indoor WLAN, a wireless local area network with a range of 15 meter, the omnidirectional antennas, this using fade path loss, you can have to calculate PT. The similar formula is there. Path loss is 20 log 10 4 pi D divided by lambda. So PT is equals to PR plus path loss. If nothing is there, omnidirectional antenna, no game, so you can just remove it uh, because it is, if it is 10 log 10 0 power. You can remove, but I'm getting the logic. What was the logic? E power. Then log T is equal to 0. So 10 power 0. Then log, log T is equal to 10 power 0. So if omnidirectional antenna is there, then T is equals to 1. So if we just the one, if you unit value is there, then log 1 is equals to 0. So omnidirectional unit gain, then the same by default. breakpoint path loss model. Like if we have this breakpoint path loss model, we saw in one of the slide. Path loss experiment is n is equals to 4.2. Path loss maximum is 120 dB. The base station range, and we know that from the formula, path loss is equals to path loss at different range dB, baseline path loss model, plus 10 n log 10 d by dV. And if we calculate with lambda, you'll be getting this. So answer is this, just a calculation it is. For ARFCN 64 lecture, it was mentioned ARFC. ARFC. It is in telecommunication, the absolute radio frequency channel number is ARFC. So ARFC is actually a code that identifies uniquely the pair of radio resources or the pair of radio frequencies used in a wireless communication, that is uplink and downlink. So it is a channel number. Absolute radio frequency number. It's a code. Okay, this concept is used in GSM, UMTS, and all. So 64 calculate the uplink and downlink center frequencies. So again, the same formula. 64 channel number is 64.2.2. This fixed values. I don't think so. The options were there. Co-channel reuse ratio. So for the cell of radius 1.2 kilometers, cluster size of n is equals to 4, find the co-channel reuse ratio is equals to, what was the formula? 3n, root over 3n. Just putting in n is over 4. It was 3.8. Even it is not depending on this radius. Now, worst case SIR. So for a 4-cell cluster with dial 1 interference at distance 7R, 13R, 19R, calculate the worst case SIR with n is equals to 3.8. So again, the same formula you have to use. SIR is equals to 1 upon 2 di by d0 root minus n, where d0 is equals to r, different r. So SIR is equals to 1 upon r. R is 7. Good told. Okay, so it is just a 7. R distance 7, 30, 19. Why it is multiplied with 2, but 4 cell. Okay, R is actually, okay, I have to see this question. I'll check, but we have to follow this formula. The values are missing. I think I've taken from some of the book. I have to check. Suppose we are having a noise figure of 10 dB and a noise floor of minus 100 dB compared to SINR. So with time and interference, it is simple formula PR divided by PN plus I. PN is equals to minus 90 dB. I is nothing but the time and interference. Again, the question is empty. But we have to calculate the summation of I, where it is equals to I1 plus I2 plus I3 or something like that. And we have to keep in this formula, and Pn is given. That is using noise figure 10 dB and noise floor, noise power KTP, noise figure. Noise floor is minus 100 dB. If the question is incomplete, I'm so sorry for that. I'll take previous year questions. This was the question, please. Let a noise figure and thermal noise of the user receiver is 10. No, thermal noise it is, okay? Noise figure. Noise figure, we know what is that. Thermal noise floor, it is N not. Of the user's receiver 10 dBm minus 100 dBm. What is the SINR of the user configuring tier 1 interface? So P of receiver C naught, we have taken 1. And Pn is equals to Pn divided by R C naught plus summation of all the interference P of R Ci divided by P of R C naught. Pn is equals to KTV plus noise figure. It is minus 90 because it's noise floor. PR or of C1 is equals to PT. This is again PT divided by 4 by D square by lambda. This is D by, because again we have to calculate from and not that power, that formula was there. Uh, Inversely proportional to 1 upon D of PC, not divided by D of Bray. Some values are missing, but you can know that how to calculate is like you have to use this formula. Four-channel reuse ratio, I was calling it Q is equals to D by R. This is equals to root over 3 then. It's very important. Which of the following can be considered as an advantage of using frequency reuse? So the same spectrum can be allocated to the other cells. Only a limited spectrum is required. Increased capacity, all of the above. Which of the following schemes enables all the user to use the entire bandwidth? It's what? It's CDMA. Because you are giving the different signature sequences to different users. Find the overall noise figure of the 4 cascaded amplifiers. So what was the formula? F is equals to F1 plus F2 minus 1 divided by G1 plus F3 minus 1 divided by G1 into G2 plus F4 minus 1 divided by G1 into G2 into G3. Right? And once you add all those, you will be getting where all values are in linear scales. In a table, it is in dB. Once you have to convert first in from linear to dB and sorry, dB to linear, and then you have to put in the values. So it's 10.13. So it is very, very similar to whenever you're calculating or solving any problem, please check first the unit. First 2 weeks are based on that. You have to first calculate, see the units. Once you can, uh, once you can, you're very sure about the unit, then we have to check. Seven. That's how it is. Okay. So which of pair of the multiple access schemes and duplexing corresponds to GSM? So first it is TDMA and first is MDD systems. In GSM, you should know these things. Like you have to remember. There's no other way. In GSM system-based system, the statement is correct about duplex filters. So the options are as GSM is TDD system. First of all, it is wrong. It is FDD system. Duplex filter is not required. Wrong. Is this GSM is FDMA system? No. Duplex filter is not required. It's required. No, it is not FDMA. It is TDM. As GSM is FDD system, duplex filter is needed. FDD is correct, but duplex filter is not needed because of that. Even though GSM is FDD system, duplex filter is not needed because uplink and downlink doesn't are scheduled non-overlapping line systems. Okay, so this is correct. So the same questions I have told, which is channel number. Using the formula, you can keep this here. This is a very good question. Radius is given. PT is equals to PR plus path loss. PR is already given. And then path loss is equals to 20 log 10, 4 pi t, 4 pi lambda by t square. 4 pi d by lambda square. Sorry. Path loss is equals to 4 pi d by lambda square. And we convert into dB. So path loss dB is equals to 20 log 10, 4 pi d by lambda. If we keep d value and lambda value, we will be getting PT. Receiver sensitivity or sometimes we call power, receive power. SNR is equals to simple energy by noise power. So simple energy is 2 into EB by M naught divided by noise power. This is the what is SNR. We have already solved these questions. Till this question is put, you can just go through this. Consider a scenario where relay node is used for extending the coverage of the base station. The relay node is transmitting with a power of 10 milliwatt, and the user measures the received power signal as minus 90. So it's the PR. If the carrier frequency is 900 megahertz and considering the free space path loss model, what is the distance between relay node and the receiver? It's not a distance between the transmitter and receiver, it is a relay node. And that too, relay node ka power is given. Okay. So again, for PT is equal to 10 milliwatt, uh, converting into the dB, it is minus 20 dB watt. PR is equals to minus 90 dB watt. FC is equals to 900 megahertz. The lambda is equals to C by FC. And we are getting 1 by 3 meter. And simply putting in the path loss formula, we will be getting that. If the gains are not given, they are assumed to be GT is equals to GR is equals to 1. So 10 log 10 1 is equals to what? See. How log 10 log curve it looks like. The log it is 1. Okay. So this is log 2x. Okay. This is log EX. Okay. Using different color. It's very important to analyze, that's why I'm telling. Say it is X. This is length of X. 1, 2, say 1, 2, 3, 4. 1, 2, 3, 4. Log X is actually increasing function. You should know that. Now log of 2 of X. Log E of x. Log of 10 of x. Okay, this is what the log functions look like. And if it is like this, so as you are increasing the base, it is becoming like that. Okay. So one more point to notice here is if it is 10, suppose it's 10. So it will come here is 1. Okay. Log of 2.4 is 1 here. Log of 2 base 2 is 1 here. Okay. So whenever we are having like this, okay, this is increasing function, right? When it is increasing, the base is greater than 1. So when base is greater than 1, what if the base is less than 1? So it will like this. It will be like this. Like this. Base is less than 1. So it is decreasing function and base is greater than 1. Increasing function and base is greater, less than 1. And the beauty is it is always like, x, it is always different for x greater than equal to 0. What if, have you heard of log of minus x? X is greater than 0 in case it is not defined. Okay. So far, so good. If you have any doubt, I just be here for more 5 minutes. Thank you so much for joining. This time, new students have joined, Asita and Girish. Can you tell me, can you please tell me about yourself? Like, are you a student? Are you faculty? Are you here in the
Hello.
class? Hi, Asita.
Yes, myself Ashita, and I am working as a HOD of in mechatronics department in Polytechnic College, and I am pursuing PhD in SVNIT Surat.
That's great. It's extended PhD.
ERS, ma'am.
Very nice. Okay. I am also a PhD student. Hmm. My
Okay,
grade
okay.
two. Yeah.
Yes, ma'am. Actually, I just want to. Can you please explain question number 15, ma'am? Not explain, only assignment question number 15.
Okay. Actually, this question is completely dependent on the lecture the sir taught. The same scenario he has taken. Maybe next time I can explain you well because I don't know. I have this solution was not sufficient for me to explain. That's why I skipped this question. I will take this in next class for sure. Sorry for this for the
Okay,
time
ma'am.
being. Yeah.
Yes.
Polytechnic College where?
Ma'am, in Nashik,
Oh, that's great.
Maharashtra. Yes.
That's great. From how long you are working?
Last 10 years.
Wow, that's great to know. Hi, Girish.
Hello, I am Girish Kadukol. I am even I have also worked in the Polytechnic earlier. Now I am working in engineering colleges from last 4 years, and even I am also pursuing the PhD on antenna designing.
Oh, that's great.
Mm. Yeah,
You are working in which college?
Jain College of Engineering, Belagavi. That is in Karnataka.
Karnataka. Okay.
Yeah.
Actually, we are. You are working in the antenna design. I am from IIT Hyderabad, and one of our project, Tihan IIT Hyderabad, is there. We are requiring some postdocs. So if you want, you can join here. IIT
That we'll
Hyderabad.
see later. For what?
Postdoc, like we are working on 5G testbed. So
Ah,
for there, we are requiring the antenna measurements and antenna specific based on USRP. So for that, we are requiring and post. We're search in search of that.
Okay,
I
okay.
think.
Sure. Just I'm pursuing the coursework now. So by next
Acha,
month
हाँ,
I
you're
have.
doing PhD. So sorry, so sorry. You're
Yeah.
doing PhD. I thought you have done that. Okay. That's
No,
fine.
no. Just so soon after that one, because last month in first week I had been to that CMR College of Engineering, Hyderabad.
Okay. Mm.
So last month I had been there. So even I worked on that CST tool also.
Okay, that's
So
great. First
from
year,
hmm.
but it's from how long you're working as an assistant professor?
Here from here in Jain College 1 year. Before this one, I was working in some engineering college only from
That's
last 3 years. Totally 4 years.
okay. Okay. Okay, thank you so much for joining. I think last class you didn't join.
Yeah,
Uh,
yeah.
that's
But
what
I'm
I.
going through the recorded video. Anyway, we have that one
Okay.
recorded video.
Anyway, these sessions are meant to be as interactive. Like it is there for doubt clearing, and because already the sir taught so many things in the class, and mostly he has taken the examples and the question number 15 also he has taken in the class. And he was
Hmm.
explained properly. That's why my aim is to build the gap, like whatever sir did teach well or focus on the concepts. That is
Hmm.
what I'm trying to do. And probability also because there are two tiers, I guess. So same things if you are teaching the same things. So it's a board for people who are joining the class. So that's why some different concepts and different content I'm trying to prepare. Anyway, thank you so much for joining and hope to see you in the next classes also.
Okay, sure. Thank you. Thank you very much. Very informative
Thank
classes.
thank you, Ashita. Thank you. Yeah.
Thank you.